So in this session, I want to talk very briefly about active galactic nuclei. And these are, kind of what their name suggests, that there is something extremely energetic that is occurring right in the core of that galaxy. So there's something in the center of the galaxy center that is outputting a huge amount of energy. This is a spiral galaxy that contains an active galactic nucleus, and we can see that it's even brighter than a similar galaxy. Whatever's going on inside the center of this galaxy is very, very bright. You can see these lines kind of coming off of this thing, these spikes in an image. Those are, again, diffraction effects from how that light interacts with the telescope. And you get these effects when the telescope is looking at something very, very luminous. There aren't actually big spikes coming off of this thing. It's just that object is so bright to the telescope that when that light interacts with how the telescope is actually built, it produces these other kind of diffraction effects. Again, these galaxies, their cores are much more luminous than all of the other light that galaxy gives off. And this is being given off across the entire electromagnetic spectrum. And about 1% of all galaxies have these active galactic nuclei. But since we know of many, many galaxies, we have lots of examples of these. We have hundreds of thousands of known examples of these active galactic nuclei. So these things give off radiation. So they emit radiation across the entire spectrum. And we'll talk about some of the consequences of this a little bit in just a little bit. And this is about occurs in 1% of galaxies. So let's look at some examples of this. A lot of these active galactic nuclei, they contain very, very powerful jets. This is Messier 87, and there is a jet of some material that's being fired off that's extending far beyond the reaches of that galaxy itself. The charged particles in these jets can reach at speeds close to the speed of light, and they can emit strong radio waves that give off radio light in these huge lobes outside of the galaxy itself. So they can produce very powerful jets. Strong jets of material. And again, for just the size of this thing, this is Cygnus A1, and the radio lobes going off of it. But this galaxy, let me zoom in just a little bit. This galaxy, if we were actually to put this to scale, that is approximately how big the galaxy is compared to the size of the jets and those radio lobes that are being given off by this thing. These are ridiculously powerful systems. Okay. Here's another example of a galaxy with one of these active galactic nuclei. This is Centaurus A. And if you could actually see in radio light, and you just looked up at the night sky, this is how large these radio lobes would be compared to the size of the full moon if your eyes were actually sensitive to radio emissions. Again, in astronomy, it's not always so much zooming in on the objects, because this one, we don't really need to zoom in all that much on these radio lobes. It's trying to detect very, very faint things in different parts of the spectrum. So again, these active galactic nuclei, they can be extremely powerful and have extremely powerful jets. This is a sequence of images taken over a few years of a blob of plasma that was ejected by one of these strong jets coming out of a quasar. We'll talk about what a quasar is in just a minute. But we can actually track how far this blob of plasma has moved over the period of years. In order for us to see this much motion in this object, this blob of plasma has to be traveling at very nearly the speed of light. Again, these are extremely, extremely strong jets. And based on these observations of how much energy it would take to launch this material out with this much, at these high speeds, this and other observational data indicates that at the center of this object, there is a supermassive black hole that is over 1 billion times the mass of our sun. Remember, for comparison, in our own Milky Way galaxy, the supermassive black hole at the center of our galaxy has about 4 million solar masses. This one would be over 1 billion solar masses. We talked about these supermassive black holes and black holes in general, saying, if I have the black hole at the center and all of this material kind of spinning in this accretion disk, kind of falling into the center, the layers of gas that are spinning around this black hole, those layers of gas are rubbing against each other. And as they rub against each other more and more, they're going to heat up to extremely high temperatures. We're going to get lots of radiation off of this thing. And when I have this spinning charged material, it can produce extremely strong magnetic fields that can produce jets out of the top and bottom of that object. That's very likely, that's kind of our lead hypothesis for what is actually causing these kinds of active galactic nuclei. So let me just kind of map that out one more time, so we know what we're specifically looking at. So we have this supermassive black hole at the center of the galaxy. So supermassive black hole. We have this accretion disk of material that's spinning around that black hole. That's kind of spinning inwards. That material goes from an extremely high temperature near the inner parts. We get very, very high temperatures near the center. So maybe I'll do this. Very high temps in the middle. Lower temps on the outside. Well, this would explain why we're getting light across the entire electromagnetic spectrum. The material near the center of this thing is hot enough and energetic enough to give off strong X-ray sources. The material near the very center, at the closest part of that jet, that might even be producing some gamma rays due to certain reaction that will happen in those intense environments. Further to the outside, we're going to have more light being given off in the visible part of the spectrum or the infrared parts of the spectrum. We get this variation on what the temperatures are at these different layers, and that will produce different kinds of light across the entire electromagnetic spectrum. So it at least hits that part of the bill. These are also occurring in the centers of these galaxies. And again, this is part of the reason why we think that these supermassive black holes are generally present in the centers of these galaxies. But they're only going to shine with this brightness if they're actively accreting material. The supermassive black hole at the center of our galaxy, there's not much gas around it. There's a little bit, but not very much. So it doesn't have this very bright accretion disk around it. So that's why the center of our galaxy is not quite going through this intense a reaction. Quasars are basically active galactic nuclei that are even more powerful. So let's talk about those real quick. Quasar is basically an even more powerful active galactic nuclei. So I'm using AGN for active galactic nuclei. So again, it's got some of the same properties as the active galactic nuclei, but just stronger across the board, much more powerful across the board. These quasars, these individual objects, they can shine thousands of times brighter than an entire galaxy. And these objects, we've got some strong reasons to suspect that these objects are smaller than our solar system. And again, these supermassive black holes, we said that the supermassive black hole in the center of our galaxy would be well inside the orbit of Mercury. Some of these larger ones would be around the size of our solar system. Let's talk about this timing of the brightness variability. When we're looking at these active galactic nuclei and these quasars, every once in a while, they'll flare up. Their brightness can increase by a few times, and then it'll settle back down. Some of these variations might only take a couple of hours. And that fact allows us to identify that these objects must be, again, no larger than our solar system. And here's why. If this whole object is flaring up, if its brightness is increasing by a factor of a few, it's probably coming from the entire object. This entire thing seems to be heating up, right? If it's going through one of these flares. Well, let's imagine what is the shortest amount of time that we could have this thing appear to get brighter for if the whole thing just started giving off more energy and then shut off immediately. What would we observe? Well, we get all of this light, basically this train of light rays coming to us from different parts of the object. So this whole train of rays of light from different parts of that source would be coming at us in, again, kind of this train style. If we're here at the Earth, even if that thing was just everything brighter, then turn it back off, the shortest time we would possibly get would have to do with how long does it take light to cross that entire quasar, to cross whatever this thing is that's giving off this light. And if we see these flares start, get brighter, and then get back dimmer again, just over the course of, a couple hours, that means this object must be at most a few light hours across, which is, again, pretty similar to the size of our solar system. And these supermassive black holes, well, the accretion disks around them could be in that approximate range for how large these things are. So again, this is why we think that it's these supermassive black holes and the jets from these supermassive black holes that produce these kinds of quasars. We see a lot of cases of quasars. We see these in spiral galaxies. We see them in elliptical galaxies. We see them sometimes in merging galaxies where both have a quasar, and we get some really interesting interactions in some of these cases. But again, these quasars are fairly rare. We don't see any nearby us. But since these quasars are so bright, they can be thousands of times brighter than an entire galaxy. Since they're so bright, we can see them from very, very far away. These are some of the most distant objects that we can actually detect with modern telescopes. But what this also means is we are seeing these quasars as they were many billions of years ago. So the fact that we don't see any quasars nearby us, it doesn't necessarily mean that, we're in some special part of the galaxy. It means these quasars were probably more common much longer in the past. So we only see them, we tend to see them at great distances. To see at great distances. And that suggests they were more common in the past. Again, these objects are incredibly bright. This is the quasar 3C273. This is the closest quasar to us. This is the original image, and when we try to subtract out the quasar's light, this is the galaxy that we see around that quasar. But again, that quasar is far, far outshining the entire galaxy that it's in. Something the size of the solar system right at the center of that galaxy is outshining the rest of the galaxy by factors of, a few hundred to maybe 1,000 times brighter than the rest of the galaxy it is in. Again, this 3C273, it's the brightest quasar. It's one of the closest, only about 2.4 billion light years away. This is an X-ray image showing the quasar and some of the jet ejecting off of that material. And this quasar, if it were in our own Milky Way galaxy, let's say it's relatively nearby us in our galaxy, if it was at the location of the star Pollux, which is 34 light years away, it would appear as bright as the sun. It's pretty fortunate that our own Milky Way galaxy does not host one of these quasars, because if that jet of radiation was aimed at us, well, that would wreak havoc on the Earth. That would basically probably eliminate all life on the Earth if we had one of these quasars aimed directly at us at that close of a range inside of our own Milky Way galaxy. Now, the last thing that I want to just quickly mention is we think that these quasars and active galactic nuclei are the result of a supermassive black hole and the accretion disk of material heating up around that supermassive black hole. Well, whether we see this thing as an active galactic nuclei or a quasar or something called a blazar, which is an even more powerful version of a quasar, it could just be a function of how are we viewing this galaxy and the accretion disk around this particular black hole. Because let's say I've got a black hole with an accretion disk around it. Okay? If that accretion disk is oriented so our view of the innermost layers of that accretion disk are kind of blocked by other parts of the accretion disk, that might be one of these active galactic nuclei, one of these things where we see that those radiolobes kind of ejecting in either direction, but we don't get quite as much of that direct radiation. If that disk were tilted a little bit, right? The same kind of a source, just that disk is tilted a little bit. Well, then we'd have a better view, a more direct view of the interior regions of that accretion disk where the material has been heated up the most and is the most energetic. That might give us our view of these quasars. And the blazars, the even more powerful versions, if we tilted that thing so that the jet produced by that supermassive black hole is aimed right at us, we are getting the full brunt of that extremely concentrated beam of radiation aiming at us. Well, that might be one of those blazars. So again, we always have to be careful of whatever the object is that is producing this effect, how are we viewing that object? If we are viewing that object edge on, or if we're viewing it face on, how is that going to affect the observations that we can take? So this is kind of the leading hypothesis on where these active galactic nuclei, these quasars and these blazars, how they are related to each other. So we'll call that one good for this session. And then in future sessions, start talking more about how do we measure the distances to some of these galaxies, because some of these galaxies we've said are, hundreds of millions to billions of light years away. So how do we measure some of those cosmic distances? We'll talk about that in the next sessions.